Okay, so in this video, we will consider our first application of orthogonal projections to the problem of a distance between a point and a line in the two-dimensional xy plane. Consider now the equation of an arbitrary line in the plane. So if you have a line, and there are two ways to write the equation of a line in generic form. You can write the equation as some multiple of x plus some multiple of y equals a constant, or you could also write some multiple of x plus some multiple of y plus some constant is equal to 0. Right? These are equivalent forms. We'll use this form. So imagine that you have this line in the xy plane given by this equation, where of course both a and b are not 0. Here's the following little fact that is very easy to prove, but really useful. The vector n, given by a being the first coordinate, b the second coordinate, has a very special relationship to the actual line L. We can give this line a name, we can call it L. And so when you see this, we're saying here's a line L. The colons mean that what this is after is the equation of the given line. So if you build a vector AB, A is whatever multiple of x you have, B is whatever multiple of y that you have. This vector is called the normal vector of the line. And normal is also a synonym for perpendicular or orthogonal. So if you say normal, also means perpendicular. So if you position the vector n in space so that its initial point is on the line, you will have a vector that is perpendicular to the line. Of course, it could be pointing up or down, doesn't matter. Either way, this vector will always be perpendicular to the given line. Let's prove this. The proof is actually quite easy. What we need is to take an arbitrary vector on the line and prove that for any such vector, it will be perpendicular to n. And of course, we prove that vectors are perpendicular using the dot product. So how can we build a vector that is on this line and an arbitrary vector? Well, the idea is to build a vector, all you need are 2 points. Let's take 2 points on this line. Suppose this is point 1, and assume it has coordinates x1, y1. And suppose this is point 2, and it has coordinates x2, y2. Well, a point is on the line if the coordinates of the point are solutions to the equation. Therefore, if we replace x and y by x1, y1, x2, y2, the equation must be satisfied. So we know that ax1 plus by1 is equal to c, and we know that ax2 plus by2 is also equal to c, because both points are on the line. Therefore, both points are solutions to the equation that defines the line. And of course, now with these 2 points on the line, we can connect them. Suppose we call this P1, and we call this point P2. We can connect them and form the vector P1, P2. Well, let us find the coordinates of this geometric vector. If you remember, when you have a vector that's built from 2 points, P1, P2, as we have right here, the coordinates are found simply by taking the end point and subtracting from the end point the initial point. So we'll have simply here, if we subtract x2, y2, if we subtract from x2, y2, y1, x1, y1, we'll get quite simply x2 minus x1, y2 minus y1. So these are the coordinates of vector p1, p2, which is an arbitrary vector parallel to the line L. The vector n is given by AB, and now we use the dot product. We know that the vector n and the vector p1, p2 are perpendicular if and only if their dot product is 0. Let's compute the dot product. N dotted with p1, p2. Well, to find the dot product, you need the coordinates of the vectors. Vector n algebraically is given by AB. Vector p1, p2 algebraically given by x2 minus x1, y2 minus y1. We can now compute the dot product. We multiply corresponding entries and we add them up. This will be A times x2 minus x1 plus B times y2 minus y1. We can distribute and see what comes out of this. We'll have ax2 minus ax1 plus by2 minus by1. Let's combine the value x1 with y1 and x2 with y2. So we'll have ax2 plus by2 and with x1 and y1, let's factor a negative ax1 plus by1. But if you just look up, because both points were solutions to the equation of the line, ax1 plus by1 equals c. And the same goes for ax2 plus by2. This also equals c. So in the end, our dot product is equal to c minus c, which is 0. And so because the dot product between n and p1, p2 is 0, automatically the two vectors are perpendicular. And this completes the proof. So every time you have a line in the xy plane given by an equation written in this form, ax plus by equals c, or ax plus by plus c equals 0, the vector given by AB, the multiple of x, multiple of y, is always perpendicular to the line. With this really simple fact, but really important, and the help of orthogonal projections, let us now solve our first distance problem. Suppose we have the following two objects, again in two-dimensional space. We have a line given by the equation 2x minus 3y plus 5 is equal to 0. And we have the point, call this P naught, with coordinates 2, 1. We will ask for the distance between this line and this point, and then we'll find the point on the line that lies closest to the point P naught. Now we write the distance using the following notation. We write d for distance, and we will always have distance problems between two objects. So we'll write simply distance brackets, and we want the distance between this object, the line, and this other object, the point. So this is simply the distance between the line L and the point P naught. Okay. Now the idea is you could draw this line in the xy plane accurately, and same thing goes for the point. And what's kind of neat here is the accuracy of the picture is irrelevant. Even if you draw your picture completely off, the idea is the same, the calculations are all the same, so you can draw a generic line and a generic point. Before we find, though, or try to find the distance, let us first make sure that we have here a non-trivial problem. And what do I mean by a non-trivial problem? Well, what if the point was on the line? The point would then touch the line, and the distance would be 0. So we have to make sure that the point is not a point on the line. Well, let's see. Let's replace x by 2 and y by 1, and see whether or not the point satisfies the equation of this line. 2 times 2 is 4, minus 3 times 1 is 1, 1 plus 5 is 6, which is clearly not 0. So this point is not on the line, and now we have on our hands a non-trivial problem. So let's draw a generic line and a generic point. And I will always draw the following picture in the same way. I'll draw my line this way, and I'll draw the point, say, up here. This is P naught. The question is, how do we figure out the distance between this point and this line? As always, for any distance problem, try and visualize the line segment whose length is the distance. And of course, if you use your intuition, this would be the segment connecting P naught to L, and the line segment would meet L in a perpendicular fashion. So the length of this segment is the distance. The idea now is, how can we use our previous result, the fact that the vector here, 2, negative 3, is normal to the line, and our idea of orthogonal projections. All we need is one point on the line. And what's kind of neat is you can take any point on the line and it won't matter. You'll still get the exact same answer in the end for the distance. So let's try and find a solution to this equation. Well, if you do it by inspection, you could take x to be negative 1, this would be negative 2, and y to be 1, you get negative 2, negative 3, which is negative 5 plus 5 is 0. So you can put this point anywhere on the line. I'll put it here for my generic picture, and I'll call this point P1. And it is my point negative 1, 1. And again, verify, plug it in, 2 times negative 1, negative 2, negative 3 times 1, negative 3, negative 2, negative 3, negative 5 plus 5 is 0. Check. This point is a point on the line. Now, we can naturally connect P1 with P naught and form the vector that we'll call U. So I'm going to call this vector U. Let us find its coordinates. The coordinates of P naught were 2, 1. So the vector U is quite simply the vector P1 being the initial point. So it's the vector P1, P naught. And as always, when you want the coordinates of a geometric vector that you want, therefore, the algebraic form of the vector, we always do the terminal point minus the initial point of the vector. And so vector U will be quite simply 2 minus negative 1, therefore 3. 1 minus 1, 0. And so we have the vector 3, 0. The question is now, how do we find the distance? The length of this line segment? Well, one thing we haven't included is our normal vector, the vector n. The normal to the line given by the coordinates 2, negative 3. And the idea is you can position the vector in space anywhere you want. The question is, where can we place the vector n so as to make the solution become apparent? And the idea is, put the initial point of vector n onto P1, keeping in mind that vector n is perpendicular to the line L. It could be pointing this way or this way. It doesn't matter. I'll make it point this way, so up. And again, it could be longer than the line segment here. It could also be shorter. It doesn't matter. So this is our vector n, which is perpendicular to the line. And now if you look at the picture, the one thing that we haven't used so far is our concept of orthogonal projections. Look at the picture. We have two vectors, vector u and vector n. If you project vector n onto vector u, you'll have a vector parallel to u, no chance of giving you the distance that you want. But what if you find the orthogonal projection of vector u onto vector n? So think of collapsing vector u onto vector n in a perpendicular fashion. So connect the endpoint of vector u to the vector n in a perpendicular fashion. And what do you notice? What we have built now a rectangle, right? Both segments meet the line L in an orthogonal fashion, and we are considering here the orthogonal projection. So we have a rectangle. And it's pretty obvious that since we have a rectangle, the distance, the length of this segment, is the length of this segment. But what is this segment? It is the projection of vector u onto vector n. So the vector right here is a projection of u, the orthogonal projection of u onto vector n. So projection of vector u onto vector, not v, but vector n. And you see, by projecting vector u in an orthogonal fashion onto vector n, we now have a vector whose length is exactly the length of this segment. Therefore, the length of the projection of u onto n is the distance between the point P0 and the line L. So all we need now is find the vector, and then the norm of the vector is our distance. Well, this is actually pretty straightforward. We have our formula for the projection. It is going to be u dot n over n dot n times the vector n. So all we need is u dot n and n dot n. Both vectors are here. Let's compute their dot products. So u dot n. As always, we multiply corresponding angles and add them up. So 3 times 2, 6, plus 0 times negative 3, 0. So we get 6 plus 0, which is simply 6. And now n dot n. Well, if you dot a vector with itself, it's the norm of the vector squared. So it's just the sum of the entries squared. We'll get 2 squared is 4, negative 3 squared is 9, 4 plus 9 is 13. So all we have now is 6 over 13 times the vector n, which is 2, negative 3. And again, from our picture, the distance, so you could call this d, the distance of this line segment, is simply the length of this vector, which is the projection of u onto n. So let's find the norm of this vector, and this will be very easy. The distance is therefore the norm of 6 over 13 times the vector 2, negative 3. Now here, be smart about this. Don't multiply the two coordinates by 6 over 13, then use Pythagoras' theorem. You can pull constant multiples out of the norm and put them in absolute value, but this is already positive, so no need for an absolute value. This is just 6 over 13 times the norm of vector 2, negative 3. And by Pythagoras' theorem, the norm of a vector is the square root of the sum of its entries squared. So 4 plus 9, but 4 plus 9 is 13. So you see the distance between the point P naught and the line L is 6 root of 13 over 13. So there you have it. The distance between the line L and the point P naught. The length of the line segment connecting point P naught with the line L. And you can see how elegant the solution was. All we had to do was take a point, any point on this line, connect the vector, the point P naught with a point on the line, forming vector u, and by projecting u onto the normal vector of the line, we have a vector whose length is the distance. And you can try, pick any other point on the line L, carry out the projection of u onto n, and you will get a vector whose length is always going to be 6 root of 13 over 13. Finally, let's ask one more question. What point on line L is lying closest to P naught? Well, you can see quite easily from the picture that the point lying on line L that lies closest to P naught is the point right here. Let's call this point Q. How can we find Q? And I claim that with what we have right now, it should be very easy. We have point P naught, and we have this vector being the projection of u onto n. How could we combine this point and this vector to obtain Q? Well, think of it now as you're standing onto this point. So Q is P naught. And now think of it. You have a vector, the projection of u onto n, that is of the right length. But if you do P naught plus vector, which is the projection of u onto n, you'll end up here. But what if you did P naught and you've added the negative of this vector? Then you would get P naught, and if you add the negative of this vector, you land exactly on Q. So it's just P naught minus or plus the negative of the projection of u onto n. And this will give you the point on L that lies closest to P naught. So let's compute this, and it's quite easy because we already have the coordinates of P naught, and we have just found the projection of u onto n. So the point Q that lies closest to P naught and is on the line is given by P naught minus the projection of u onto n. The point P naught, if you look up, has coordinates 2, 1. So it's 2, 1 minus the projection of u onto n, but that is just 6 over 13, times the coordinates 2, negative 3. If you want to combine these two as a single point, put everything over 13 and factor the 1 over 13. So here multiply by 13 over 13, so you'll have 13 times 2, 13 times 1, therefore 26, 13, minus the vector 2, negative 3. So it's 1 over 13 times 26 minus 2, 24, 13, negative 3, 13 plus 3, 16. And if you want the point as a single point, not as a scalar multiple of a point, multiply through, and you have 24 over 13, 16 over 13. And there you have it. The point Q that lies on the line closest to P naught is the point 24 over 13 for the x component, 16 over 13 for the y component. And in the end, there's a very simple way of verifying that you have the right point. The point Q is supposed to be a point on the line. So it should be a solution of the equation of the line. Let's check that our point Q solves this equation. So it was 2x minus 3y plus 5, and this should be equal to 0. Let's substitute. So 2 times that, 2 times 24, 48. So we have 48 over 13 minus 3 times 16 whoops, what did I do here? Oh, I left over my 6. Aha. This makes more sense, because this was not going to work. Now it's just 6 times that. Let's fix that. So what are we going to have? We'll have 26 minus 12. That will give us 14 over 13. And 13 minus 6 times negative 3 is plus 18. 13 plus 18, that's 31 over 13. Now we're talking. So the point Q is 14 over 13, 31 over 13. Sorry about that. Now, but you see, in a sense, this is what you should do. I made a mistake. I got the wrong point. And just by checking if the point was a solution to the equation of the line, just like that, I spotted that I had made a mistake. Let that be a lesson to you. Now let's check. 2 times x, sorry, 28 over 13, minus 3 times 31 over 13, that's negative 93 over 13, plus 5. Well, 5 over 13, well, if you want this over 13, multiply by 13 over 13. 5 times 13, that's 65. But 28 minus 93 is negative 65. So you get negative 65 plus 65, both over 13. And of course you get 0. And now you know that you have the right point on L that lies closest to the point P naught. So always when you find this point, check whether or not the point solves the equation of the line. If it does, you're pretty darn sure that you have the right point. If it doesn't, you've made a mistake somewhere. Either you did like I did, you've left something behind, or maybe you made a mistake in your projection vector. Either way, it's always worth checking.